Mark your own. Who's my favorite student? Sadly, none of you. Oh, Anne. How much momentum, magnitude, and direction? Did this say how much impulse? No, it said how much momentum. Momentum, symbol P, is just mass times velocity. So it's going to be 80 times 22. I can do that in my head. It's going to be 160 plus 60 is 176. Is that right? Yes? 176 kilogram meters per second. That's the magnitude. This also wanted... I forgot a zero. Not 176. It's 1,760, Mr. Dewick, showing off doing math in your head, and you're off by a factor of 10. Wow. Kilogram meters per second. Direction. So I would give you half mark for the magnitude, half mark for the direction. A says, find the change in momentum, magnitude, and direction. Okay, change in momentum is, I can find that a bunch of ways. You know what? I saw an initial velocity and a final velocity. I said, I'm going to use mv final minus mv initial. But I also saw south, and south. Is there an actual change in direction here? So I don't need to let one way be positive and one way be negative. I'll let south be positive, just to make it easy. So it's going to be m 220, 52 minus 220, 23. Did you all get 6,380? Direction? Because it did say magnitude and direction. Must be the same as the velocity. 6,380 kilogram meters per second south. You know what, Mr. Dewick? Let's be clever. This is why I really like digital ink, because now I can fit it onto the page. What's the magnitude of the force which acts upon it? You could go F equals ma, because they gave you m. You could find A and go F equals what, ma, and I'd give you full credit. But because I found impulse, I think I'm going to try saying force is also impulse over time. Impulse is force times time, and I got the F by itself. So it's going to be 6,380 all over 58 divided by 58. And I get 110 newtons. It just wanted the magnitude. By the way, on the previous one, I would give you half mark for the magnitude, half mark for the direction. A skier moving forward at 18 meters per second lets go of a tow line. What is the magnitude of the impulse? Okay. Impulse. I don't see a force or a time. I think I'm going to use mv final minus mv initial. And in this case, v final is 0. So mv final is 0. Minus v initial is, m, 80. V initial is 18. Can I do that one in my head? Well, 1,600 minus 36. Is it 1,660? No, 564. I'm off. I'm way off. Or maybe I'm not clear. 0 minus 80 times 18. Should I have trusted myself? 1,440. I was off. Wow, way off. Oh yeah, 160, not 16, Mr. Duke. Now, why is it negative? By the way, I said magnitude, and the negative implies direction. So if you gave me a positive answer, I won't take the half mark off. But what's the negative telling me here? The skier needs to lose momentum to come to a stop. Yeah, they do. Of course they do. Units, kilogram, meters per second. Yeah.
So I said a positive that number backwards.
Yep. Because I just said magnitude. I didn't ask for a direction.
Oh.
Right. B is asking me to find time. Well, you know what? If impulse is force times time, I guess time is impulse divided by force. I guess. It's going to be my answer from part A, 1,400 divided by 270. Now, if you put the negative in there, you would actually have to make the force negative, because if the impulse is backwards, you know which direction the force is? Backwards. Because time is positive. That's going to be this divided by 270, and I get, I'm going to ignore the negative, 5.3 seconds. Is that right? Did I make a mistake? Yeah? That's right. Oh, I wrote 14,400 instead of 14,400. And I did the same thing here for some reason. So this is why I use my answer button, because even if I write something down, I can still, fluke isn't the right word, I can still get the right answer because I've taught myself, be careful on here. So 5.33 seconds, I would take 5.3. I would not take 5, I would not take 6. Yet another way to find time. We've got a bajillion of those. Am I going to memorize it? No. If I need it, I got it. Next page. Ooh, 2 marks. Impulse. I guess it's going to be change in momentum. I see an initial. I see a final. Ooh, but you know what else I see? East and west. I need to let one way be positive and one way be... Okay? What do you want to let be positive? Okay. I'm fine with that. Little trick of the trade, by the way. I will often let the final be positive, because that way I'll get a minus minus in my initial, which I'm better at doing math in my head when it's positive, but that's such a nitpicky thing. I don't care. So you said this is positive. I would make a little note. Positive, negative. I'd put a big negative in front of the 43. And it's going to be MV final minus MV initial. It's going to be M 0.17. 170 grams is 0.17 kilograms. V final negative 43 minus M 0.17. V initial positive 22. And I get... negative 11.05 equals 11.05, 11.1. I would take 11.0. I would take a half mark off because it's definitely 11.1. Kilogram meters per second. What direction is negative? I would give you half mark for the magnitude, half mark for the units, 1 mark for the direction. West. Ooh, now they want the average force, magnitude and direction. I guess if I get a negative, the force will be west. If I get a positive, the force will be east. You know, I think the force is going to be west because the puck was coming in from the east and it got turned around and is now heading west. I think the only way you can do that is to apply a really big force to the west. So I'm pretty sure I'm going to get west as an answer. But let's see. I think I'm going to use force equals impulse over time. It's going to be negative 11.05 over 0.025. and I get negative 442 newtons, which is 442 newtons west. Again, 1 mark for the answer, 1 mark for the direction. I take a half mark off if you missed the units or something silly like that. If you got A wrong, but for part B, you went that answer divided by 0.025, and you got an answer here, and your answer is west, I would give you 2 out of 2 for part B, even though it's the wrong answer. A baseball is thrown due east with an initial velocity. Okay, it's struck by a rebounds due west. If the ball is in contact and the average, find the impulse. You know what? I think here I'm going to find the impulse by going force times time. But before I go any further, I see easts, I see west, I see a change in direction. Okay, Kate, which way do you want to let be positive? Okay, so Kate let west be positive. So that means this is going to be negative. Which way was the force applied? If this ball ended up going west, I think that's negative. I think the force has to be negative. I know. I think the impulse is going to be negative 20,400 times 7.5 times 10 to the negative 4. Now, if you let east be positive, that's totally fine. Our directions will still match. Negative 20,400 times 7.5 times 10 to the negative 4, and I get negative 15.3. So that's going to be an 15.3 Newton seconds. You could say kilogram meters per second here because I went force times time in my brain when I looked at the units. Oh, Newton seconds, but I would take full credit for kilogram meters per second. Direction. What direction did we say was... Sorry, Mr. Dewick, you let east be negative, so west should be positive. I'm sorry, Kate. I totally did that backwards. I should have let west be positive because you said west was positive, didn't you? And the force is to the west. That's what made the ball bounce backwards to the west. I would get a positive answer. Well, that was terrible explaining, Mr. Dewick. And I'm going to get that. It is to the west, is my point. I would give you 1 mark for the 15.3, 1 mark for the west. Final velocity. Okay, I think what I'm going to do here is a little strange. I'm going to go impulse equals impulse. I'm going to go 15.3 equals mv final minus mv initial. I want to get v final by itself. I think the 15.3 is going to drop down like a domino. I'll plus mv initial. I think I'll divide by m. I think that's v final. Never done that one before, but I think so. Let's see. It's going to be 15.3 plus, what was the mass? 0.15. What was the velocity? Negative 39. All divided by 0.15. Bracket 15.3 plus 0.15 times negative 39, close off the top, divided by 0.15. You all get 63? I got a positive 63. So it did say magnitude and direction. Kate, which way did you let be positive? If you had let east be positive, you would have got negative 63. Negative east is definitely west. For 3 marks, I would give you 1 mark for the magnitude, 1 mark for the direction. I would give you 1 mark if I saw somewhere that you'd clued in you're going to go 15.3 equals MV final minus MV initial. What's the answer to number 6? Why is it 0? Impulse means a changing velocity. If you're at a constant velocity, impulse is a changing momentum. If you're at a constant velocity, is your momentum changing? Can you give yourself a lovely score, please, out of 15? If you need to lawyer with me, now is the time. Called conservation of momentum. Very, very fundamental law of the universe. But first, in the collision seen below, which vehicle experiences the larger force? We're going to vote. So we can vote on the truck, the car, or both the same. Who says, Mr. Duick, the truck experiences the bigger force? The truck does, because it's bigger. Got 1. Who says, no, Mr. Duick, the car is going to experience a bigger force because it's going to get creamed? The car. No one. Who says they're both the same? Really? How on earth can that be correct? Okay. Forces come in pairs, or if you want to, you could write newtons first, second, third, third. Okay? The force between these will be the same. Well, why is it that the car and the car driver are almost always worse off as a result of this collision? Yeah. Okay. Same force. Let's draw a little line like this. Big mass, small acceleration. Small mass, big acceleration. Does that work as my explanation? You'll figure out what we're getting at. And it's acceleration that does the damage. I need to give you a term. A closed system is a system that is cut off from the outside world. It has no net external forces. There's no invisible angel pulling or pushing from off the screen. There's no F applied. Some examples would be frictionless surfaces. Once you let go of a curling rock and you're letting it go, assuming there's no friction at all, that would be an example of a closed system. There's no forces, no external forces acting on it. Deep intergalactic space in a vacuum. Systems floating on the water. And objects that are rolling. We're going to be looking at closed systems. For collisions in a closed system where there's nothing pushing from outside, the contact forces are governed by Newton's third. Forces come in pairs. So forces are equal but opposite. But Lena, that also implies that momentum change. What's another word for momentum change? Let's write underneath that in brackets. Impulse is also equal and opposite. Why is that? Well, forces come in. In this collision, I'm going to argue that both of them have the same time of collision. So if I multiply by time, that's the same value for both of them if I do it to both sides. And I get force of the object 1 times its time has to equal the force of the objects 2 times its time. You know what? That means the impulses are the same except one's positive and one's... Okay? The magnitudes are the same. What does it mean to say that momentum change is equal and opposite? If the car loses 20 units of momentum, what happens to the truck? And what that means is the amount of momentum you start with will be the same as the amount of momentum you finish with. There's a fancy phrase or word for that in science. We say that momentum is conserved. If you start off with 1,200 kilogram meters per second of momentum before the collision, do you know how much momentum you're going to have after the collision? 1,200 kilogram meters per second. Momentum for a system is not gained or lost. It's transferred from one object to another. Usually because momentum is mass times velocity, and the masses aren't changing, it means at least one object in a collision is going to change its velocity. Which, Callie, is kind of Captain Obvious. Well, yeah, I've seen collisions, but here's the physics of why that's the case. Yeah, you can turn the page. Ooh, example 4 says this. If conditions are such that the car and the truck end up at rest after the collision, how can we say that momentum was not lost? Well, if they end up at rest, what's the final momentum of the truck if it's at rest? What's the final momentum of the car if it's at rest? So what's 0 plus 0? You know what the total final momentum was? You know what the initial momentum was? Has to be 0. Now, how can that be? Okay, so this is my argument. Final momentum, so I'm going to say the initial momentum equals the final momentum. Let's put vector signs on them. And what was the final momentum? 0. What's the initial momentum? Before the collision, are both vehicles moving? Look at the picture, yeah? So I'm going to say M truck V truck initial plus M car V car initial. That has to equal 0. How the heck can that be? What's the mass of the truck? What's the initial velocity of the truck? What's the mass of the car? Anyone? 1,000? What's the initial velocity of the car? Negative 24, because they're in opposite directions. Does that work? Do you get a 0? Yeah, you get positive 24,000. Take away 24,000. This is how we were able to say that momentum was conserved. You had no momentum to begin with. The total momentum to begin with, because momentum is a vector, Lena, was 0. And you know what the final momentum was? Give me the punchline. 0. Momentum was conserved. If we had run the numbers and there was 100 kilogram meters per second when we added these together, you know how much momentum there would be afterwards? 100 kilogram meters per second. This collision would be skidding to a stop because it would still have some velocity. Ooh. This is the law of conservation of momentum. A fundamental law of the universe. One of the biggies. In any collision or explosion, let me say that again. In any collision or explosion, in any jeune, is the dumb way I remember it. Momentum is, what's the fancy word? Conserved. Marcus, this means that momentum is not created, not destroyed, but transferred from one object to another. The total you start with will be the total you end with. The law of conservation of momentum can be written in several ways. It can be written in English. The total initial momentum of a system equals the total final momentum of a system. I will never write it in English because that's too much words. You may notice I tend to abbreviate. You can write it as the momentum of object 1 initial plus the momentum of object 2 initial equals the momentum of object 1 final plus the momentum of object 2 final. We'll be looking at two car crashes or 2 object crashes, collisions. You can easily extend it to 3 or 4 or 5. We're not going to bother, but you can write it like this. Who knows what that thing is, it's a Greek letter.
So,
It's the Greek letter sigma. And what does it mean?
so,
The sum of, or the total. The total momentum you start with equals the total momentum you finish with. Or, since momentum is what times what? You can look at your green sheet and answer. Momentum is what times what? Mass times velocity. You could write it as m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. All of those are different ways to write the law of conservation of momentum. Which of those is the shortest? Which of those do you think Mr. Dewick is more likely to use? Which of those also has Greek letters, which make Mr. Dewick feel a little nerd cred there? So I'm going to write that. Here's what I mean. We use the law of conservation of momentum when there is a collision or an explosion, when there is a jeune. A wonderful example of conservation of momentum. Oh, how will I abbreviate conservation of momentum? Have you spotted it already? See them? A great example is a toy called a Newton's cradle. So I'll leave my Newton's cradles out for the remainder of the unit, and if you're good little boys and girls, you can play with them. In fact, you can even ask Santa Claus for one in your stocking, maybe. Example 5. I like example 5. Although I'm going to give you these not as pictures, but as word problems. But this is what we've been building towards. We can now analyze collisions. Zach, what does example 5 want me to find? Which one is missing? Look at the pictures. You'll figure it out. Which one, initial or final? Now, there's a symbol for later in physics. It's an apostrophe. We actually read that as a prime. We would say VA prime, but you know what? After final. Okay, this wants us to find VA final. Is there a collision? Yes? This is a job for conservation of momentum. I'm going to write this. The sum. Oh, by the way, look up. A Greek letter sigma is supposed, don't write this down, supposed to look like that. But most people get kind of sloppy and they just draw a capital M on its side, which is what I do. So you can draw it as nice or as messy as you want. The sum of all the momentum that we start with has to equal the sum of all the momentum that we finish with. This is the law of conservation of momentum. I looked at the picture. It looks like they've labeled these mass A and mass B. Zach, before the collision, what was moving? Mass A, mass B, or both? Stuck together or separate? So I'm going to have the momentum of car A initial and the momentum of car B initial. Wham! They collide. After the collision, what's moving? Car A or car B or both? I heard someone say car B. I heard someone say both. Which one is correct? Why both? How do you know? Well, if they're asking me to find VA final, it's probably not 0. Are they stuck together or separate? I think they're separate. So I'm going to have momentum of car A final, momentum of car B final. There's my setup. Looking at this picture, are there any changes in direction? No. Oh, yeah. Means what? Well, let's call to the right positive. Ooh, this 2 here, Zach, what? Yes, because the arrow's pointing to the left. Don't know. Positive. So if I get a negative answer, my direction is going to be to the left. If I get a positive answer, my direction is going to be to the What am I trying to find? Zach, what am I trying to find? Where is that hidden in which of these four terms? Well, let's go one step further. From your green sheet, momentum is what times what? And this is not change in, this is not impulse. So I guess this is going to be MVA initial plus MVB initial. Wham, they collide. And I should be careful, MA and MB, so I don't get them mixed up, right? MAVA final plus MBVB final. Zach, what did you say I'm trying to find? That bad boy right there. All right, let's get it by itself. What side is it on? So what's going to drop down like a domino? The whole left side. MAVA initial. We're going to write out in our notes every single step. As you get good, will you be able to cut corners and take shortcuts? Yes. On a test, will you cut corners or take shortcuts? No. But let's write it out in our notes. Plus MBVB initial. Okay. What am I trying to get by itself, Zach? How? Oh, move this whole thing over? I got to be fussy. It's not the final velocity. It's final momentum. Subtract the MBVB final. So minus MBVB final. I like that. I like that. So that would take care of that. How would I deal with this M? What's this M doing to the velocity? There's a plus sign right there? What? What? Oh, it's timesing. I agree. So how will I move that M over? Now that's a pretty big rewrite. Don't kid yourself. But apparently that equals, and if you don't mind, Zach, I'm going to put the VA final on the left by itself where we're used to seeing it instead of putting it on the right. That will tell me the velocity of car A after the collision. What we're really saying is this. Here's all the momentum we started with. Some of it was absorbed by car B. What's left went to car A, and then to find its speed, divide by its mass. Now we're at the plug and chug stage. Numbers. Zach, what was mass A? I've scrolled down. Sorry? What was VA initial? Plus, what was car B? What was VB initial? What? Sloppy mistake. Okay, and I'm kind of glad you did that so I can point it out, but I'm kind of grumpy you did that because we even put the negative in there, didn't we? Did you not put a little negative right there to remind yourself? You should have. Keep going, my friend. Minus, what's MB? I guess 2,000. What's VB final? I think the picture told you. Double check, positive or negative. Oh, are you positive? Shut up. Okay. And 1,000. Hey, time to get your calculators out. Definitely brackets around the top. What do you get? I think I do this in my head. It's going to be 10,000. Take away 4,000. That's 6,000. Take away 8,000. That's negative 2. Do you get negative 2? So 2 meters per second direction. What are we saying here? If I go back and look at this original collision, I'll let the tennis ball be car A. The little green brain is car B. I guess they were heading towards each other. Look at the arrows. They crashed. Afterwards, car B bounced forwards. Car A bounced backwards. Boink. Okay. Let's do another one. Yeah. Quick like a bunny. Like I got what, two, three more. Yep. Okay. Is there a collision? This is a job for conservation of momentum. What are they asking me to find? It looks like VA's initial, how fast car A was going at the beginning. Okay. So, the sum of all the momentum we started with equals the sum of all the momentum we finished with. Is there a change in direction? You know what, Lena? I'll call this negative. I'll call that negative. I'll call to the right positive. You could do it the other way around, but I think we're more comfortable letting right be positive. Okay? Lena, before the collision, what's moving? Car A, car B, both, or neither? I think both. Stuck together or separate? I think separate. So what can I write? Don't write this down, look up. Don't write this down, look up, but do look up. Keep looking up. I could go, don't write this down, momentum of car A initial plus momentum of car B initial, but maybe I can skip that step because, Lena, momentum is what times what? From your green sheet, you got it on there. P equals, huh? See where it is? Yeah. Momentum is. So I think, pick your pencils up. Let's see if we can go to that line. In other words, I'm going to see if I can skip this line and go straight to this. Let's see. Before the collision, they're both moving. So, Lena, I'm going to have mass of car A, velocity of car A initial, and plus mass of car B, velocity of car B initial. Bam! They collide. Mr. Dewick, are you going to do that on every collision? Maybe. You look a little tired, people. After the collision, Keegan, what's moving? Car A, car B, both, or neither? Look at the picture. Car B? What about car A? Both. Stuck together or separate? How do I know they can't be stuck together? Because they have different velocities. If they're stuck together, their velocities would be the same. Okay? So I'm going to have mass of car A, VA final. Mass of car B, VB final. You okay with that, Keegan? Alrighty. Hey folks, what are we trying to find? Which one? Okay, I'm trying to get that by itself. What's going to drop down like a domino? This time, the whole left side. Yes? What else? I want to get this by itself. I guess I need to move this thing over. Minus MB V initial. So that takes care of that. Now I need to deal with this mass. What's this mass doing to the V? So? Apparently, that'll tell me how fast car A was going. I would say leave a gap and just continue where we are right now and get what you missed later. Because now I've scrolled down, plug and chug. Lena, back to you from the diagram. What's the mass of car A? I've scrolled down. What was it? 1,000 again? And velocity of car A, -2. Yes, negative. And then there's a plus sign. Was car B 2,000 again? Okay. Final velocity of car 2, 4. And then take away car B 2,000 again. Initial velocity of car B -3. Looking at the arrow, negative, yes. All over, Lena, what was car A, 1,000? Okay. What do you get? I can do this one in my head. It's going to be -2,000 plus 8,000. That's 6,000. Ooh! What do you get? The 12? Yeah. Sorry? Is it 12? Yeah? Okay. Direction. How do I know? Positive. Or you could call it east if you wanted to, whatever. Let's do one where they stick together. I think in the after, they're stuck together. Look at the picture. Okay? So, is there a collision? This is a job for conservation of momentum. I'm going to start out by saying the sum of all the momentum we start with has to equal the sum of all the momentum we finish with. Looking at my velocities, are any of them negative? One is. Got to be negative because look which way it's pointing, right? Looks like this car was backing up. Yeah? Alrighty. Before the collision, what's moving? Car A, car B, both or neither? Both, stuck together or separate? So I'm going to have mass of car A, velocity of car A initial, and mass of car B, velocity of car B initial. Wham! They collide. After the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? Look up. Right? Treat them like one big car. You could separate them too, but I think this will be a little cleaner. So if they're stuck together in brackets times the same velocity. What are we trying to find? Okay. Nick, what's going to drop down like a domino? What side is the VA initial on? The. So what's going to drop down like a domino? The right. Yep. All you had to do was say the right side. I'm good with that. Let's do that. in brackets, MA plus MB VF. Oh, that's a terrible vector sign, Mr. Duke. And then, Nick, I'll deal with the MA in this, but I need to move this over. How would I move this? Well, what's this doing to the V? So, yep. And then how would I get the V? How will I move the M over? How will I get the V by itself? What's the M doing to the V? It's multiplying, so I think you said divide? Yeah. By the way, are you going to try and memorize all these? No. I think I gave you just the conservation of momentum law on your sheet, right? Did I have the sum of all the momentum initial equals the sum of all the momentum final? Yeah, that's what I gave you. All right. Nick, I've scrolled down. What was, let's see, in bracket, what was mass A? Hopefully the picture says. 2,000. What was mass B? 4,000? Oh, they changed the masses. What was V final? V final? And then minus 4,000. What was VB initial? -3? All over. And MA you said was 2,000? What do you get? You really want to practice doing these on your calculator, because although these ones have nice numbers and you might be able to do them in your head, I can't. Usually they won't be as nice. It's going to be 30,000 plus 12,000, 42,000. Is it 21? Yeah. Positive or negative? Positive, so what direction? So what happened in this collision? In this collision, if we go back and we look at the numbers, car B was going backwards at 3 meters per second. Car A came slamming in at 21 meters per second. They stuck together and they moved off forwards. Okay. By the way, which car is heavier? Car B. Which car experienced more owie than car A, because it would have gone through a bigger acceleration, because F equals what? MA. One more. When I was a kid, when we jumped off of our bike and let it roll and then ran and caught up to it, we called it ghost riding. Do they still call that, or is no? Bikes. We have video games. Shut up. When I was a kid, we had to ride our bikes. Okay. And so what we would do on a flat road is you would pedal at medium speed. You would jump off, see if your bike would keep going for a while, and then you would try and run and hop back onto it before it fell down. That was our little game. Man. Some of you are just like, I never thought of that. Jeez. Okay. I guess let's use R for rider and B for bike. This isn't a collision. They're breaking apart. It's an explosion. It's a slow explosion, but an explosion is when objects break apart. They definitely separated. Okay. This is a job for conservation of momentum. Mud, before the collision, what's moving? The rider, the bike, both, or neither? Stuck together or separate? So I guess it's going to be mass rider, mass bike, V initial. Wow! Afterwards, both and separate, yes? So it's going to be mass rider v rider plus mass bike v bike. I didn't put finals on these. I could, but I noticed I only had the one initial, and these were I think we're okay. Because what do we want to find?
What else do you like?
How?
Drop
Sure. And do you mind? I'm going to put the V on this side by itself. By the way, how fast was the rider traveling before he or she jumped off? How fast are they traveling now? Did the rider lose momentum or gain momentum? So what's the bike going to do? Gain. The bike's going to be going faster than 5. So if you're really paying attention and visualize what's going on, there are some built-in error checks along the way. If I got an answer less than 5, I've messed up. Let's plug in our numbers. Mud, what was the mass of the rider?
60 kilograms.
Bike?
20.
VI was 5?
Yep.
Minus 60, was it 2?
Yep.
All over 20. So this is going to have brackets inside of brackets, brackets around the top, and then bracket 60 plus 20, close bracket, times 5, minus 60 times 2, close off the top, divided by 20. Error. Where's my error? Wow, I should have done a double bracket. That's sloppy, Mr. Dewick. 14? And to the right. That's the law of conservation of momentum. It says the momentum you start with equals the momentum you finish with. That was also a lot of me talking. I get that. We're going to do another lesson tomorrow. We're going to finish off the unit tomorrow, and then we can take Thursday and Friday and quizzes and review and quizzes and review. So you'll get time to work on this, but your homework, you can certainly try number 1, number 2. I'm probably going to assign all of these. Number 3, number 4. Yeah, we got Calvin and Hobbes, 5 and 6, so we'll have a bit of fun with that as well. Tomorrow is going to be the same as today, but you're not going to have pictures. You're going to have word problems. And then we're done the unit on momentum, I think. Oh, no, then we got explosions. Sorry, and then we're done the unit on momentum. Quick, like a button. Well, there's like 6 minutes. Yeah, go ahead. I talked a long time.